Hello, everyone. Welcome to my presentation on modeling SATA Texas complexity. My name is Salan Patroradom. I am a PhD student at Drexel University. This work is under the supervision of Dr. Nagarajan Kandasamy and Dr. Yanis Savidis. Just to give a quick summary of this paper, recently logic obfuscation has emerged as a countermeasure to hardware security threats, but a well-developed analytical framework for security evaluation is underdeveloped. So in this paper, we address this gap by proposing an analytical framework that quantifies resilience against a SAT attack. The approach that we use is, first, we model the attack resilience as computational complexity of a search problem. We then develop a probabilistic model to address variations in the search paths. In doing so, we assume equally likely path selection to avoid bias from a specific experimental setup of the attack. For today's presentation, we will start with some background on the logic lock circuit and the SAT attack. Then we will discuss the limitations of the current evaluation framework and the proposed solution. Then I will give you some examples of the use cases before we conclude. In the global supply chain, hardware production is often outsourced to some third parties, but some partners may not be trustable. So researchers have proposed logic locking and IC camouflaging techniques to prevent potential security threats. These families of techniques aim to make the circuit behavior harder to understand by obfuscating the circuit Boolean functionality. Next, we will define what logic obfuscation does to our circuit. Logic obfuscation introduces some uncertainties to the original circuit. In this half-adder example, after logic locking, the truth table of the original circuit expands to include multiple columns. The rows are the primary input patterns, and each cell entry is an output vector. The original column is hidden among the many possible Boolean functions, which correspond to the key value, which is also the column header. There will be at least one correct key column, although multiple correct columns are possible in some circuits. And incorrect columns will have at least one row with a corrupted output pattern. A logic lock circuit will have additional inputs, which is the key vector k. However, k is an internal signal. The correct key value will be loaded to an on-chip tamper-proof memory. Only the primary inputs x are directly controllable, and the primary outputs y are directly observable. However, the internal secret key value can still be figured out by an attack guided by an oracle. First, along the supply chain, an obfuscated netlist can be obtained. Second, once the IP owner configures the key and releases the activated live IC to the market, the adversary can buy the activated live IC, which now behaves as the original circuit that we refer to as the oracle. By observing each input and output pair, some incorrect candidate columns can be ruled out. So if enough observations are used, then the adversary can tell which key column is the correct one. However, it is actually slow to prove a key pattern is correct because we will need to use all the input-output pairs. On the other hand, it is fast to prove a key is incorrect. For example, this input-output pair rules out the last two columns. With a set of some input-output pairs, it is possible to reject all the incorrect keys, so only the correct key columns remain. Thus, to minimize the effort, the adversary goal is then to reject all the incorrect key columns instead. But how to efficiently construct such a set of input-output pairs? The example set on the left uses only one observation, row number 4, whereas the one on the right uses 3. The constraint learned from these 3 input-output pairs on the right are redundant, thus inefficient. What we have here is actually a set cover problem, where the goal is to find a set of observations row set Ri that has the same cover as the union of all the row sets. The member of the row set are the rejected key patterns. There are multiple solutions in which the adversary would prefer using less observations, which means less effort spent. One efficient algorithm is the Boolean satisfiability-based attack, or the SAT attack for short. The algorithm iteratively picks a useful row, one at a time. A row is useful if it will help remove at least one more incorrect columns that have not yet been eliminated before. On the example on the right, after using the second row, R2, picking R3 as the next input-output pair will not be useful, since it won't help reject any new columns. On the other hand, if we pick row 4, 6, 7, or 8, these have at least one pair of different output patterns. So at least one column will be rejected, whichever of the two. Such a useful input is called distinguishing input pattern, or DIP for short. DIP can be found efficiently by using a set solver. Then the process repeats till no more DIPs can be found and only the correct key columns remain. This flowchart summarizes the set attack algorithm. First, we formulate the Boolean formula in conjunctive normal form. Then we call a set solver to find a DIP. If the DIP is found, then query the oracle, append the constraint, repeat till no more DIPs can be found. Then we finally pick the correct key. In the example on the right, there are 8 choices for the first step. The set solver that we use may pick any of the 8. Suppose a second row is chosen. After querying the oracle, the first 2 columns remain. Next, there are 4 valid second DIP choices. Suppose the solver picked row number 4, query the oracle. Now, the third DIP cannot be found, so the attack is done. So we can pick any remaining columns at the correct key. The preference or bias in DIP selection depends on multiple factors, such as how the CNF formula is arranged, which set solver is used and how it is configured, and also whether or not simplification is done on the formula at some point. Given the attack algorithm, we can define resilience measure using the computational complexity. Typically, resilience is measured in terms of the total time to solve, T, or the number of iterations, lambda. The iteration here refer to the loop shown in yellow. So the number of iterations is the same as the number of the set solver calls, the numbers of DIP used, and also the number of queries made to the oracle. The total time is approximately the sum of the time used at each iteration T sub I, averaging the individual time T sub I. The total time is then scaled by the factor of the number of iterations, lambda. The T average depends on the set solver call time, which is an NP complete problem, and also the time used by oracle query, and also the time to append the constraint. Consequently, T average depends on the complexity of the circuit topology. Lambda, on the other hand, abstracts out the circuit topology and captures the information on the search space itself. So in this work, we focus on lambda as a proxy for set resilience measure. Given the same pair of a locked circuit and the oracle, it is possible for lambda to vary. Here we have 2 different search paths with lambda equal to 2 and lambda equal to 1. Such variation of lambda complicates resilience evaluation. The search path taken depends on which assignment of X is found first by the set solver. Next, we will talk about the limitations of the current evaluation practice. Typically, when proposing a logging technique, the authors report the number of DIPs and or the time to solve. The values are from an experimental evaluation by launching the set attack once or multiple times. Due to multiple search paths and possible variation of lambda, some of the studies using low numbers of set attack trials may misrepresent the security strength. Second, large key size tend to be used in order to exhibit the timeout. However, using large key size make a single set attack trial takes longer. As a result, when projecting security trend, less values of key sizes are evaluated and reported. Thirdly, to ensure exploration of multiple search paths, set attack should be implemented in a stochastic manner. The detail on whether or not the implementation is deterministic or stochastic is usually left out from the report. Molecular experimental approach can be achieved by ensuring adequate search space exploration. However, in this work, we are proposing an alternative approach, which uses an analytical framework instead. First, we capture variation of lambda via a probabilistic model, treating lambda as a random variable, find its distribution, then derive the statistical measures for lambda. The proposed analytical evaluation framework has 4 steps. First, determine search space truth table U. Second, extract all search path DIP sequences. Third, fit the DIP selection probabilities. And fourth, compute the PMF of lambda and the corresponding statistics. For a given pair of a locked circuit and the oracle, a truth table denoting whether or not the output is uncorrupted can be derived. That is what we call the U search space truth table. Since multiple pairs of a locked circuit and an oracle may map to the same U table, we should actually analyze U rather than each circuit pair. The use truth table captures all the possible search paths while leaving out the details on the circuit topology. So we can think of U as a search space, and to analyze lambda, we can analyze U. From a user space table, we can enumerate all possible search paths. A list of all diff sequence is shown on the bottom, which can be visualized as the tree on the top. The numbers in the tree nodes are the row numbers. For example, the diff sequence 3 then 4 search path is shown in red. Each branch is a use of a single dip. If we formulate dip selection as a random process, we can derive the probability of the set attack taking a certain search path. After assigning the branching probabilities, the dip sequence tree then becomes a probability space. Since each experimental set attack setup has an arbitrary dip selection preference, to avoid a bias, we assume the dip selection to be equally likely. However, after dip selection, probabilities can be used in other scenarios. The search path length lambda is now a random variable. Probability of lambda equal to 2 is then the sum of the probability of the dip sequence search path with the length of 2. The probability mass function of lambda can then be put together, and any statistical measure can then be derived. For proper notation, let's define the random variable for lambda as the uppercase D for search depth. Let's look at the first use case. Here, the goal is to derive some closed form expressions for sub-resilience for an out-of-cone locked circuit. For out-of-cone logic locking, some primary outputs are corrupted by some flip signals at the XOR gate. The consequence is that the functionality of the original circuit is arbitrary. The use space will then look the same. This allows us to characterize resilience strength with respect to the locking technique itself for any arbitrary original circuit. So we can analyze the use space instead of the functionality of the original circuit pair. TT-lock, tenacious, and threshold logic locking is chosen as the subject of the study for this paper. At key size of 2, the use space and the dip sequence for TT-lock is shown here. Assuming equally likely branching probabilities, we can compute the PMF and the statistic of lambda, or the random variable D. The distribution here looks similar to the discrete uniform distribution, except for the last case being combined into the one before. Repeating the analysis for other values of key size, we get the PMF with a consistent pattern. We can also observe that the dip selection process is similar to a random sampling without replacement. So with all the hints, we can finally derive the closed form expression for the PMF and the statistical measures in terms of the variable key size K. The second use case is to study how resilience increase after an insertion of a key gate for some in-cone logic locking technique. For an in-cone locking, key inputs are intermingled with the original main logic cone. In this example, some XOR key gates are inserted into some of these candidate insertion points. Here we consider 12 locations, as shown in the purple circles. Unlike out of cone, the resulting use space after insertion depends on the circuit netlist topology. So we have to evaluate resilience case by case. The closed form approach is not suitable here. This plot shows cumulative resilience after we insert a key gate one at a time, construct a new use space, then derive the new PMF, and find the mean. For example, the third data point is from after insertion of 3 key gates at location 7, then 1, then 5. The last data point is when all the locations are used, so it makes sense that we get the maximum achievable resilience here. However, if we choose the next iteration point to always maximize marginal resilience gain, then the maximum achievable value can be achieved much earlier with only the use of 7 key gates. In this use case, equally likely assumption is used to make the sample mean consistent as compared to if we use Monte Carlo instead. To conclude our presentation, we first propose a probabilistic model to capture variation of lambda. The PMF illustrates more about lambda than using the sample mean alone. Second, we propose the use of equally likely assumption to avoid dip selection bias. No set software is used in the analysis. For other set attack variants, it is possible to use different values for branching properties. The same framework can still be applied. Finally, in the use case number 1, the framework is used to derive closed form resilient expressions. In the second use case, we use a framework to quantify marginal resilience gain. Thank you for attending my presentation and have a good day.